really interesting, X-linked peptide mapping algorithm. So we're looking forward to hear you. Thank you.
As Carl already discussed the level of protein structure, primary, secondary, and how his future research can help define and build the tertiary structure, my talk goes beyond the tertiary structure into quaternary structure, how those tertiary structure interact with each other, as well as protein complexes, how heterogeneous complexes interact with each other, and how we can actually use mass spectrometry to detect those stable interactions. So this is a tool we've been working on, X-linked peptide mapping algorithm, X-linked cross-link. Let's start with protein. If we say protein is playing central role in the cellular machinery, it is affecting the works of DNA replication, DNA repair, everything. It is affecting works of RNA splicing, its transportation, and protein gets affected by environment and phenotypes. So protein is an important part of the cellular machinery. And so when protein is important part of cellular machinery, the one protein do not really function as its own, especially when it comes to DNA damage repair or DNA replication, DNA transformation. There are protein complexes involved, and it is important to understand how those complexes are physically interacting and which part of interaction is occurring at which place. Those kind of studies can be done using many methods. We have classical 2-hybrid assays, affinity chromatography, immunoprecipitation. One of such methods is cross-linking. And cross-linking, if I try to define it, it's a process of joining peptides with the help of cross-linkers, which are just a bifunctional small molecules with a linker arm. And then it can be coupled with other methods to replace mass spectrometry as well as mass spectrometry to really analyze the cross-link product and find out what is the pattern of cross-linking between different proteins. What is typical cross-linking mass spectrometry pipeline, in short CXMS pipeline, look like? So we have two proteins. We add the cross-linking we have two proteins, we had cross-linking and let them react with each other, and that give us certain kinds of cross-linking. That means covalent bonding between the cross-linker or small molecule and the protein. And this only captures stable interaction and not transient interaction. So it's not the case that you will get lots of false positives, because transient interactions are really abnormalities in most of the cases. And then we digest it, resolve on the gel, and we can see mainly three types of cross-linking. This is called type 0, 1, and 2, where cross-link has nothing attached to the second end of the cross-link, where both ends of cross-links are attached to the same peptide, and here cross-link attached to different peptides. We run the mass spectrometry, typically random mass spectrometry, even in certain cases MS3 is being done, where mass spectrometry, then ETD, and then CID, because ETD is known to break disulfide bond, and then those separate peptides can be analyzed using CID, and then the data gets analyzed, and we see the result. So this step, data analysis step, is really bottleneck of this problem. The mass spectrometry instrument is getting better and better, more sophisticated, but we are not improving the data analysis. And so my research deals with this part, improving the data analysis part, really interpreting what mass spectrometry is giving us. Advantages of this method is there is no practical limit on size of protein or its structure. We can work with anything, and it really requires femtomole amounts of protein, and it does not require any complicated experiments. It is straightforward biochemical experiment, and with advances in mass spectrometry instrument, the analysis is becoming really accurate and really efficient. And we have a variety of cross-linkers to really different sizes of cross-linker, different properties, specificity to different amino acids. So we can really capture different properties within the crossing gaps. So what is the problem really I'm talking about in data analysis? It's the complexity of data. First of all, low abundance of cross-linked species, because when we get the mass spectrometry data, it contains non-cross-linked species and cross-linked species. And cross-linked species probably consist of only 1% of entire spectrum. So the first task is really to identify out of entire spectra which spectrum is representing cross-linked species and non-cross-linked species. The other part is, as I said, there are three simplest type of cross-linking possible, type 0, 1 and 2. And then there are combination of 0 and 1, 1 and 1, 1 and 2. It makes very complicated. And then non-specific cross-linker. You don't know that that chemical is going to bind to which amino acid. It can bind to any of the 20 amino acid. And the cross-linked spectra, as it contains two peptides, it usually has double the charge compared to a single peptide, which makes analysis even more difficult. What is the solution? First, improve data quality, and MS Instruments are doing really good job in improving the data analysis and data quality. And second thing, improve the data analysis, and I'm trying to do a good job via bioinformatics. So why the cross-linked peptide is unique? Simplest representation. This is simple peptide and this is cross-linked peptide. And low abundance, non-linear product, high charge and different specificities of cross-linkers. So is everything bad with cross-linked peptides? Not really. Because when we are doing the cross-link experiment, we know which protein we are working on. The sequences of protein are not unknown. They are known to us. And we can use that fact to our advantage in deciphering the spectra for the cross-linked peptide. So what the problem looks like when we have a simple protein spectrum, it's just a haystack. Just blindly pick a hay and try to characterize that what's the length, what's the composition, what's the amount of carbohydrates is protein in it, and yes, we are done. But when we have cross-linked peptide, so it's like finding the needle from the haystack, but not finding the needle of the haystack like looking at it, but when you are blindfolded and you just don't have to find the needle, you also have to characterize it. What does needle contain? What is the length? What is the composition of iron, nickel, whatever it is? See, the complexity is twofold. It's like double needle in the haystack problem, if I say in the same language. And it's mainly because of the fact that non-specific cross-linker exist. We don't know this detail. It can bind to any of the 20 amino acids. These are some of the types of the cross-linker, but this is the major problem in dealing with. We have database search method available when we are dealing with conventional mass spectrometry of the proteins. So we have a database of all the proteins, and when we get the mass spectra, we compare it to the database, and when we find the match, get the score, and bingo, we are done. What's the problem with cross-link mass spectrometry? It contains two peptides at a time. So database becomes of the size of n square, astronomical. And again, so you see the distribution of trypsin, like most of the, when we digest the peptide with trypsin, most of the fragments are equal to or less than the length of 20. So we are looking at a combination of 20 amino acids. But in the cross-link peptide, when we have two such peptides within same spectra, we are actually looking at the combination of 40. So it's n square, and then we have to look for larger combinations of amino acid. If you just look at 20 amino acids, there's 69 billion possibilities. We have this big database, it gets really complicated. The other thing we have is de novo sequencing. When we start from, we don't worry about anything about the sequence or protein or database. We start with whatever is there in spectra. We start with the numbers and not with the biology. So suppose we have this sequence MGI-VTR, and we see these spectral ions, B and Y ions in CID spectra. We just get the difference between two ions, and if the difference between B3 and B4 is 99, and that's why we have a valine over here. Simple. When it comes to cross-linked peptide, well, it works fine. We have methionine, lysine, isoleucine, and then, ooh, there's a difference of 487. What amino acid is that? Well, that is the amino acid with extra baggage of the other cross-linked peptide. And so that's where this method fails. The other difference we have is charge. In the fragment spectra, charge is not known. Either we try to predict the charge or deconvolute the charge, or we check for the possibility of all the possible charges. When we have charge less than or equal to 3, even if we check for all possible charges, we have just 3 options for each spectrum. When we have charge greater than or equal to 4, and in some cases up to 8, for each of the peak, we have to check for 8 possibilities. So even deconvolution gets real tough. Again, what comes to our advantage? We know the protein sequence. We know the protein sequence, what we are working with. And so to answer this question and get rid of these difficulties, we come up with XLPM, X-linked peptide mapping algorithm. And due to time limit, I am not discussing the algorithm in detail, but I was happy to share if someone like. But in general, if I describe XLPM, what XLPM does is it starts with the protein sequences and it assumes that any amino acid of one protein sequence can interact with any amino acid of other protein sequence. It can cross-link with any amino acid, all the possibilities. Then there is a user input, that what kind of cross-linker they have used, what kind of modifications they have used, digestion enzyme, and we have spectra. These are the filter that's been used over the course of this algorithm, which filters down and point out to right cross-link species. Once we have those right cross-link species, it gets compared to the tandem spectra or fragment ion spectra, and while comparing to fragment ion spectra, it gets scored. So typical pipeline would be, we have protein sequence and mass spectra, we find out potential cross-link candidates while filtering down using all the input parameters, and then score the cross-link peptide while observing whatever fragment ion spectra we got. And this is one unique thing we did here, is we developed a filter called BY-ion filter, so that we are not really using the entire spectrum of a peptide to score it. Instead, we are using the subset of the spectrum, but we are getting the result of the same efficiency. What is BY-ion filter? It's a very simple observation that the detection of a particular B ion with the charge less than that of precursor ion implies high probability of detection of complementary Y ion with remaining charge. It is, I mean, in the sense of chemistry, it looks obvious, but it is more than chemistry. It is the power of the instrument. It's a detection, and it's not really the production. That's why it becomes important. So we analyze. This is the observation, and we analyze the data available in the National Institute of Standard and Technology. They have very good data, and each data point is done with 10 replicates, so it's quite reliable. To find out whether this observation is true or not, we analyzed all the data and we plotted it for all the charges. So charge 2, charge 3, charge 4, and with charge 5 and higher. What it says is Y ions to B ions ratio. Which Y ions? Complementary Y ions with remaining charge. If our observation is false and no complementary Y ions with remaining charge is present, then Y is always 0, and this ratio, everything will look like 0, a big peak at the 0. But that's not the case. You can see a distribution, and that's why our observation is not incorrect. We can see the distribution, and it's not perfect because we cannot see a single peak at the 1, that all the complementary Y ion with remaining charge was present. It's somewhere in between, but still it is usable. These values are median value for each charge, and we actually take these values into account while we score for our spectra. This is the scoring method we are using. It's basically an extension of percentage match. So it's number of B, it's a fraction of B ion and fraction of Y ion. But as we are not looking at all the Y ion, that fraction get corrected by that median value. We just observe from the NIST data. We validated our software on 3 systems with 3 specific purpose: disulfide bond, DSS, which is specific cross-linker, joins lysine to lysine, and SDL it can join lysine to NE. The purpose of the first is to compare if the XLPM's effectiveness compared to other good software, StarOX, and we chose StarOX because it is producing really good results compared to the tools available right now. Here, one of our collaborators solved a crystal structure of ring 1, so we analyzed the actual crystal structure, whether we are predicting the right contact point using XLPM, and here we shown its efficiency in resolving when the specificity of the crosslinker is not known. Comparing to StarOX, we can clearly see that XLPM did better job in predicting more crosslink peptide. More important is we expect crosslink peptide to be charged higher than 3, greater than or equal to 4. And as we can see, XLPM predicted a higher fraction of higher charge spectra compared to StarOX. It predicted just 1 out of 8, and XLPM predicted 12 out of 20. So we definitely did a good job. Another part is we analyzed ROC curve, where we fed a wrong information to the XLPM stating that disulfide bond is possible not between cysteine to cysteine, but cysteine to any amino acid. So if we get disulfide bond between cysteine to alanine, that is supposed to be false positive. And using this data, we plotted the ROC curve, and you can see it's pretty good ROC curve with the area under curve of around 0.97. This is the actual crystal structure of rim1, and these 4 residues, lysine 64, 29, 86, and actually lysine 105, but crystal structure is only salted 104, so that's why we are taking that into reference, are predicted to be the most available surface amino acid, and you can see they are really available on the surface. Another thing is we use DSS for this cross-linking, and DSS has a linker length of 11.4 angstrom. And if we analyze the highest scoring entry from lysine 86 to lysine 29, it has a length of 9.5 angstrom, while lysine 86 is on the flexible loop. So it can possibly accommodate a linker length of 11.4 angstrom. This is a very flexible loop. So XLPM did a good job in explaining the contact points for the structure. And again, if you see resolving the site of cross-linking, you see here it's a cross-linking between rim1 to PIF1. rim1 SDA was specific, connecting to lysine and N-terminal. And for PIF1 side, it can connect to any of them. I'm just showing the 2 of it. It predicted actually 18 cross-link species. I'm just showing 2 of them as an example. You can see the difference. It says that N-terminal is more likely to interact or to react in cross-linking compared to the 5th amino acid, and that's correct, because N-terminal in the structure, N-terminal is really pointing out. If we have a dimer and N-terminal is pointing out between them, so N-terminal is available, and 5th amino acid is really buried down within the interface of dimer, so it's not available to interact with any other protein. If you see the same thing for resolving when we have non-specificity, this is what we would ideally like to see, because when it comes to spectrum, there is really difference of only, we are considering B and Y and so on, so there is only difference of 2 peaks, and we really like to see this increment in the score to be certain that this peptide probably interacting via C terminal and not any part of N. We have a website, you can use it if you have data to analyze. We have limited option in the website. The algorithm has no limitation on cross-linker or digestion enzyme or modification. Website is limited. You want to use other options, you can mail to us and get original scripts from us, and you can use by yourself, or you can just mail your parameters and we can include the parameters within our website for yourself. This is the structure of the website. Basically, the job manager runs all the time, checks whether the job is running or finished, and when we have available slot in the queue, it gets the input file from the queue and it submits to XLPM. And it uses MySQL database in the background, and when the job is finished, it mails results to the user. This is our future plans. Right now, XLPM has limited functionality. It can only analyze protein-protein interaction and CID data. We'd like to increase it to the ETD data and protein DNA RNA interaction. And also, we are increasing its functionality from analyzing a pair of sequencing to analyzing entire proteome, mainly by using peptide sequence tag and Bayesian scoring methods. So right now XLPM is here, and after we extend it, XLPM will be there with full functionality and analysis of full proteome. This is the validation system we are using. We have primary and metastatic kidney cell from the same patient, from melanoma cells, and we are doing cross-linking and cross-linking to validate our proteome level functionality of XLPM. And this is typical workflows. We will analyze data, we have charge deconvolution, generate the PST tags and do the data research, and here we'll be again using PYI. With that, I would like to acknowledge my advisor, Dr. Sibello, Nathan, Michael, and Roger. They helped with some part of the project. Dr. Verghese and Dr. Okulan, they solved the crystal structure for Ring1. Dr. Rene and Raman, they have done some background work in generating the pure proteins we have used. And Yongden, Yunfei-Chen, Cheryl, Dilipji, and Dr. Jennings, they were really the person who ignited the idea to develop this tool. And I'm grateful for the support from this tool in present my work. Thank you.
Yeah, was there a specific reason why you choose RIM1? Because I know it's involved in yeast longevity, or was that just something random? That's the first question. And the second question is, what are Y ions?
So we chose Ring1 because one other area our lab is working on is to understand mitochondrial DNA repair. And Ring1-P1 complex is one of the important part in mitochondrial DNA repair. So we have already been working with Ring1. That's why we chose Ring1, because we had some knowledge and we can validate it better because we are knowing the function and the functional pathway and series of events involved with Ring1 and P1. The other thing is B and Y ion. When we use tandem mass spectrometry, the peptide gets fragmented at the amide bond. And when it gets fragmented at the amide bond, the N-terminal part is known as B ion, and the C-terminal part is known as Y ion.
Okay. Cool.
I have a question. So you have shown the validation part of your algorithm. Are there any? Did you have a big data set for validation, and what about did your algorithm predicted everything well, or were there false predictions or something?
That's why area under the curve was 0.9708, so there were definitely false positive in the data. The another problem is we can only do that for disulfide bond and non other, because really except for disulfide bond, the standard data doesn't exist. So even if you predict something, it's very difficult to tell whether they are false positive or real positive. So we can do that for the disulfide bond because it has been studied long and we know that each disulfide bond is. So it wasn't perfect. DMC was 0.9708. There were some false positives, but it's still better. 0.97 is a good number. Yes.
Yeah, and one question is, you said you validated. I mean, you are basically predicting what amino acids are interacting. How do you validate it if you only depend on mass spectrometry data? So what other method do you have to validate whether what you predicted is actually what's there?
So we predicted, like in case of the same I'm saying disulfide bond, we already know from the literature that disulfide bond between which residues exist in the BSA is pretty standard sample. So we can compare our result with the literature, whether we have predicted right or not.
Okay.
In case of Ring1, we have the crystal structure. We can see whether those contact points are really available for the interaction or not. If they are right buried into the protein, then it is predicted wrong.
Cool. Very interesting.